Okay, dear students, in this class I am going to discuss about the second application of Ampere Circuit Law, that is solenoid. In previous class already I discussed about what is Ampere Circuit Law and equation of Ampere Circuit Law and the magnetic field due to the long straight current carrying conductor. You get the equation V is equal to mu naught into I divided by 2 phi r. In this class again I am going to discuss the second application of Ampere Circuit Law, that is solenoid and magnetic field due to the solenoid. Already in your 10th classes in the topic electric current, all this concept already you have studied, but once again I repeat the introduction concept of solenoid. Solenoid means it is a long cylindrical coil. It is a long cylindrical coil. It consists of closely packed circular loops. It is a long cylindrical coil. It consists of closely packed circular loop. Then it is called solenoid. It is a long cylindrical coil. It consists of n number of closely packed current carrying loops. Closely packed current carrying loops. Then it is called solenoid. Here this is the structure of solenoid. This is the structure of solenoid. Solenoid, it is a long cylindrical coil. It consists of closely packed current carrying circular loops. When the current is flow inside this solenoid, the magnetic field is produced. The magnetic field is produced inside the solenoid because it is insulated wire. Because it is insulated wire. Here, inside the solenoid, at the center of the solenoid, the magnetic field is maximum. The center of the solenoid, the magnetic field is maximum and it is uniform. At the end of the solenoid, the magnetic field is non-uniform, and outside the solenoid, the magnetic field is zero. This is very important. Outside the solenoid or outside the ideal solenoid, the magnetic field is zero. Inside the solenoid, at the center of the solenoid, the magnetic field is maximum. At the end of the solenoid, magnetic field is half of its center. Half of its center. Solenoid means it is a long cylindrical coil. It consists of closely packed circular current carrying wires. And ideal solenoid means if the length of the solenoid is greater than its radius, then it is called ideal solenoid. The length of the solenoid is greater than its radius, then it is called ideal solenoid. Or your length of the solenoid is much more larger than its radius, then it is called long solenoid. Due to this solenoid, the magnetic field is produced. Due to this solenoid, the magnetic field is produced. Now, we will find the expression for the magnetic field due to the current carrying solenoid. When the current is flowing inside the solenoid, the magnetic field is produced. But at the center of the solenoid, it is insulated wire. Here the insulated wire is wounded along the cylindrical tube. The inside the solenoid or the center of the solenoid is magnetic field is maximum. At the end of the solenoid is magnetic field is not maximum. At the center of the solenoid, along its axis, the magnetic field is uniform. But at the end of this solenoid, the magnetic field is not uniform. And outside this solenoid, the magnetic field is zero. This is very important. Now, I am going to discuss about the magnetic field due to a current carrying solenoid by using Ampere Circuit Law. In the last class already I discussed about the Ampere Circuit Law. It states that the line integral of the magnetic field due to the current element is equal to mu naught times of net current enclosed by the path. This is the equation of Ampere Circuit Law. From using that Ampere Circuit Law, here we find the magnetic field due to the solenoid. This is the cross-sectional view of the solenoid. The cross-sectional view of the solenoid. Imagine when the current is flowing in this solenoid. The current is flowing in this solenoid. The magnetic field is moving in this direction. The magnetic field is moving in this direction. The current is moving in this direction. Current is moving in the form of helical path, or it is also called a circular path. When the current is moving in this direction, the magnetic field is moving in this direction. They are perpendicular to each other. This is the cross-sectional view of the solenoid. Cross-sectional view of the solenoid. Here, this line indicates the direction of the magnetic field. This line indicates the direction of the magnetic field, and this is the cross-sectional view of the solenoid. When the current is moving in this solenoid, the magnetic field is produced inside the solenoid, not outside. The magnetic field is produced inside the solenoid. To find the magnetic field due to this solenoid, here I considered as Amperian loop, rectangular as a Amperian loop. Amperian loop means it is the closed path around the current carrying wire. The closed path around the current carrying wire or the current carrying conductor is called Amperian loop. Here I find the rectangular Amperian loop. I draw the rectangular Amperian loop to find the magnetic field inside the solenoid. Here, the rectangular Amperian loop. This is AB, B to C, C to D, and D to E. This is the Amperian loop. Amperian loop means it is a closed path. It is a closed path around the current carrying wire. This is the rectangular loop. Rectangular Amperian loop. From using this rectangular Amperian loop, now we find the magnetic field due to this solenoid. And this sign indicates, this into mark, this sign indicates the current is perpendicular to the direction of magnetic field. This is the direction of magnetic field. And the current is moves perpendicular to the direction of the magnetic field and always directed inward the plane of the paper. This current moves inward the plane of the paper. This diagram here, this moves, the current moves into the plane of the paper, and this dot diagram indicates the current is moved outward the plane of the paper and it is perpendicular to the direction of magnetic field. This into mark indicates the current moves into the plane of the paper, or the current is perpendicular to the direction of the magnetic field and moves into the plane of the paper. Moves inward the plane of the paper, and this dot diagram indicates the current is perpendicular to the direction of the magnetic field and moves outward the plane of the paper. It is an imaginary concept. It is imaginary concept. Here this is the one circular coil. You have one circular coil. Just wait. This is a long cylindrical coil. Just imagine this is a long cylindrical coil. It consists of n number of turns. When the current moves inside this solenoid, at the end of this, inside this solenoid, and the current is emerges at this point, the current moves inside and the magnetic field is moving in this direction. This is perpendicular to the direction of the current. Here this into mark indicates the current is perpendicular to the direction of the magnetic field and moves inward, and the dot mark indicates, this indicates the current is perpendicular to the plane of the paper and emerges outside the plane of the paper. Here, these types of wires are closely packed along this solenoid. This is a very important concept. Solenoid means it is a long cylindrical coil. It consists of closely packed n number of current carrying wires. Due to that n number of current carrying circular loops, the magnetic field is produced. Now, I am going to find the magnetic field due to the current carrying solenoid by using Ampere Circuit Law. When you use the Ampere Circuit Law, here I draw the rectangular Amperian loop around this solenoid. Here A, B, C, D. This is the rectangular Amperian loop. From Ampere Circuit Law, we know the equation. From Ampere Circuit Law, the line integral of magnetic field B dot dl is equal to mu naught into net current enclosed by the, in this diagram, net current enclosed by the rectangular loop net current enclosed by the rectangular. The line integral of B dot dl. Here the line integral from A to B, B to C, C to D and D to A. Then I write this equation. The line integral of ABCD. The line integral of rectangle ABCD into vector B dot dl is equal to mu naught into net current enclosed by this rectangular loop. Here I is the current in this solenoid and N is the capital N is the total number of turns in this solenoid. That how to calculate the total number of turns in this solenoid? The total number of turns, capital N is the total number of turns in this solenoid. From using the equation N into L, number of turns per unit length and length of the solenoid, or small n is equal to capital N divided by L, the number of turns per unit length. From using this value you can calculate the net current enclosed by the rectangular loop. ಅದು ಎಷ್ಟು ಉದ್ದ ಇದೆ, ಅದರಲ್ಲಿ ಎಷ್ಟು ನಂಬರ್ ಆಫ್ ಟರ್ನ್ಸ್ ಅದಾವೆ, ಅದರ ಮೇಲೆ ಏನಾಗಿರುತ್ತೆ ನಮಗೆ ಇಲ್ಲಿ ನೆಟ್ ಕರೆಂಟ್ ಎನ್ಕ್ಲೋಸ್ಡ್ ಬೈ ದ ರೆಕ್ಟಾಂಗ್ಯುಲರ್ ಪಾತ್ ಕಾನ್ಸೆಪ್ಟ್ ಡಿಪೆಂಡ್ ಆಗಿರುತ್ತೆ. If the number of turns in the solenoid is maximum, the magnetic field produced due to the solenoid is also maximum. If the number of turns in this solenoid is minimum, then the magnetic field is also very small quantity. If the number of turns increases in the solenoid, when the current is flowing in the solenoid, the magnetic field is also increases. If the number of turns inside the solenoid is increases, the magnetic field is also decreases. This is the very simple concept. Magnetic field is directly proportional to strength of the current. If the current is increases inside the solenoid, the magnetic field is also increases. If the number of turns increases around that solenoid, the magnetic field is also increases. Then here the line integral of ABCD is the rectangular path B dot dl is equal to mu naught into net current enclosed by that path. Here the net current I, it is depends on N into L into I. This is equation number N. 1. N is the number of turns per unit length. L is the length of the solenoid. I is the current in the solenoid. Here the magnetic field depends on all these three values. The magnetic field depends on number of turns per unit length and length of the solenoid, and I is the current flowing through the rectangular loop. The total magnetic field depends on all these three factors. Here the line integral of ABCD vector B dot dl is equal to mu naught N L into I. Now we will find the magnetic field for this line A to B, and for this line B to C, and for this line C to D, and for this line D to A. Here the current flows from point A to B along the direction of the magnetic field. Along the direction of the magnetic field. In the first case, this is equation number 1, and for the line AB, magnetic field for the line AB. Only now I find the magnetic field due to this line AB. Here, this line in this rectangular path is along the direction of magnetic field. For the line AB, or you can divide this equation as the line integral of B dot dl is equal to the line integral of AB into vector B dot dl, the line integral of BC into vector B dot dl, or you can write as the line integral of A to B, B to C vector B dot dl, and the line integral of C to D vector B dot dl, plus the line integral of D to A vector B dot dl. Magnetic field due to the line AB, magnetic field due to the line BC, magnetic field due to the line CD, and magnetic field due to the line D to A. Then after that combine all the magnetic field. It is the vector sum of all the value. First, for the line AB magnetic field, the line integral of AB vector B dot dl is equal to the line integral from A to B, it is vector B dot dl is equal to, for this line only, according to the Ampere Circuit Law. Then you write this equation, the line integral of AB into B dl cos theta. It is in the form of A dot B. A dot B is equal to AB cos theta, and A to B, for this line A to B, here the theta value is, for this line A to B, theta value is 0 degree. Theta value is 0 degree, then cos 0 degree value is 1. Then you get the line integral of A to B vector B dot dl is equal to, here B is a constant, then the line integral of A to B into dl is equal to, when you are integrate this dl, you get the equation B into L, equation number 2. The sum of this length is, that is length of the solenoid, equation number 2. You get this equation B into dl. Theta equal to 0 degree, cos 0 degree value is 1. The line integral from A to B, vector B dot dl is equal to B into, it is a constant value. When you are integrate any value, take the constant value outside, you get only the line integral of A to B into dl. Integration of dl is L. Integration of dx is x. And integration of dl is L. We get the value B into L. This is for only for the line A to B. Then for the line B to C, for the line C to D, and for the line D to A. But here, for the line B to C and for the line D to A, B to C and D to A, here integration or integral value of B to C and D to A both are perpendicular to the direction of this magnetic field. B to A is perpendicular to the direction of magnetic field, and D to A is, this is the perpendicular to the direction of magnetic field. Now I find at a time both the values here. For a line BC and DA, magnetic field due to the line BC and DA, ಇಲ್ಲಿ ಸ್ಪೇಸ್ ಕಡಿಮೆ ಇರೋದ್ರಿಂದ ನಾನು ಎರಡನ್ನು ಎಟ್ ಎ ಟೈಮ್ ಫೈಂಡ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ನೀವು ಎರಡನ್ನು ಸಪರೇಟ್ ಆಗಿ ಕೂಡ ಫೈಂಡ್ ಮಾಡಬಹುದು ಅಥವಾ ಎರಡನ್ನು ಎಟ್ ಎ ಟೈಮ್ ಕೂಡ ನೀವು ಫೈಂಡ್ ಮಾಡಬಹುದು. For a line BC and DA, then the line integral of BC vector B dot dl is equal to the line integral of dA into vector B dot dl is equal to, B dot dl is equal to, here the line integral of B dot dl is equal to the line integral of B dl cos theta, the line integral of B dl cos theta for this value. But here at this condition theta is equal to 90 degree. Theta is equal to 90 degree. For the line B to C and D to A, these two lines are perpendicular to the direction of the magnetic field. Cos 90 degree value 0. Cos 90 degree value is 0. Then magnetic field due to BC and DA value is 0. Then for a line BC and DA value, this value becomes 0. This is equation number 3. Magnetic field due to the line BC and magnetic field due to the line DA, that value becomes 0 because these two lines are perpendicular to the direction of the magnetic field. And the next one is for a line C to D. For a line C to D. For a line C to D, here the line integral of CD vector B dot dl. Here we write C to D, or also we can write in the form of the line integral of C to D. Vector B dot dl is equal to, vector B dot dl is equal to 0 because magnetic field outside the solenoid is 0. Magnetic field outside the solenoid is 0 because insulated wire is wounded on that circular or cylindrical coil. Only the magnetic field inside the solenoid is present. The magnetic field outside the ideal solenoid is 0. At the center of the solenoid, the magnetic field is maximum. At the center of the solenoid is magnetic field is maximum, and along its axis it is uniform. At the end of the solenoid is the magnetic field is present, it is non-uniform. Outside the solenoid, the magnetic field is 0, and this is the reason outside the solenoid from C to D, again the magnetic field is 0. This is equation number 4. Substitute equation 2, 3 and 4 in equation number 1. Substitute equation 2, equation 3 and equation 4. All these values in equation number 1. The line integral of B dot dl is equal to mu naught n into L into I. Mu naught n into L into I. The line integral of B dot dl is equal to, it is the line integral of A to B, B dot dl value is, that is B into L. B into L. The line integral of B to C B dot dl value is 0. Then the line integral of C to D B dot dl value is 0. Then D dot dl value is 0. Then BL is equal to mu naught n into L into I. Mu naught n into L into I. Here L and L get cancelled. Finally, we get the result. B is equal to mu naught n into I. B is equal to mu naught n into I, which is the expression for magnetic field due to the long straight current carrying solenoid by using Ampere Circuit Law. It is a very simple concept. This is the Ampere Circuit Law. The line integral of vector B dot dl is equal to mu naught into net current enclosed by the rectangular loop. This rectangular loop depends on N value, number of turns per unit length. L is the length of the solenoid, I is the current in the rectangular loop. When you are dividing all these four cases separately, you get the values. In the first value only you get the maximum magnetic field. Here C to D and D to A, these two lines are perpendicular to the direction of the magnetic field. When these two lines are perpendicular, theta value is 0. Cos 90 degree value is 0. Then C to D, this is the outside the solenoid. Outside the solenoid, the magnetic field value is 0. Then you get the equation B is equal to mu naught n into I, which is the expression for magnetic field due to the solenoid. What is solenoid? Solenoid is a long cylindrical coil. It is a long cylindrical coil, or it is a long coil. It consists of closely packed circular loops or closely packed current carrying circular loop. Then it is called solenoid. If the length of the solenoid is greater than its radius, then it is called ideal solenoid. Then the magnetic field outside the ideal solenoid is 0. The magnetic field at the center of the solenoid is maximum and it is uniform along its axis, and magnetic field at the ends of the solenoid is non-uniform. Magnetic field at the ends of the solenoid is non-uniform, and the expression for the solenoid magnetic field due to the solenoid is B is equal to mu naught n into I. Magnetic field depends on the number of turns per unit length, and magnetic field due to the solenoid depends on current flowing in that solenoid. This is the second application of Ampere Circuit Law. In the next class, I will discuss about the third application, that is magnetic field due to the toroid. Thank you.